Hello, I'm John Ratsey, and welcome to my presentation about diversion structures and intakes for spate irrigation. We'll start by discussing the need to manage sediment. Sediment is a fundamental feature of most spate irrigation schemes. It is both a benefit because deposited sediment creates fertile land with good water holding properties, and it is a problem because clogged canals and structures, rising fields and command levels. Therefore, development of a strategy for managing or living with the sediment is the first requirement in planning work on a spate irrigation scheme. We'll look at sediment composition. We have fine sediment, which is supply controlled with factors such as soil conditions, land cover and rainfall intensity in the catchment affecting the quantity and type of the fine sediment. Once in suspension, fine sediment is very slow to settle out. Coarse sediment is controlled by the waddy and flow conditions upstream of the diversion point, and coarse sediment settles out as the velocities reduce. Here, this graph shows typical composition of sediment. We have a relatively small proportion of bed load, which is gravel, cobbles, boulders, and maybe coarse sand. We have a suspended load, which is also sand, but will very quickly settle out if the flow conditions change. And we have the wash load, which is silt and clay. Now, the wash load is very slow to settle and effectively cannot be excluded, whereas bed load and suspended load are excludable. So our sediment management options. For the coarser sediment, we can manage it by exclusion, which is to prevent the sediment from entering the intake, by ejection, which is removal of sediment after it's entered the canal, or by trapping, which is the collection of sediment in a basin on the canal for subsequent removal. Finer sediment should be transported to the fields, where it usually improves the soil. For sediment entering the canal system, the amount of sediment entering the canal system will be reduced by limiting the maximum flow. This then reduces the sediment intake by reducing the volume of water with the maximum sediment load that goes into the canal. And the sediment intake can be calculated based on an assumed flow to sediment load relationship and the flow entering the intake, and adjusted for the exclusion efficiency, which is the proportion of the sediment load that actually gets excluded. This graph is an example of a calculation. We have two different catchment conditions of larger and smaller catchments. As in my previous talk, a small catchment tends to have a much greater peak to volume ratio on the hydrograph. Now, this point on the graph shows that by making the intake 30% of the maximum flow, we can reduce the sediment diverted down to about 70% of the total. So for sediment exclusion, in addition to closing or restricting the intake, we can achieve sediment exclusion by capturing the cleaner surface water which flows to the outside of a bend. We can design the intake with a low divergence angle and also minimize turbulence, which raises any bed material into suspension. And we can provide a sluiceway to flush sediment downstream from the intake. And we can provide a weir in front of the intake to separate some of the bed material from the surface flow. Now, we have some design options for sediment management. We have a basic intake without a weir, here called Type A. Our sediment management strategy: first, locate the intake on the outside of a channel bend. Second, to limit the flows entering the canal with a flow throttling structure. If gates are provided, to close them during periods of very high flows, and to provide the canals with sufficient slope to keep medium to fine sand moving, and minimize ponding, and use flow division structures. And we need to make provision for rising command levels as sediment is deposited in the fields, and we need to consider arrangements for and the sustainability of any canal clearing or periodic bank raising to accommodate sediment deposition. We can have a Type B intake, which can have a low weir, so it is like the Type A intake, with a skimming weir in front of the intake, a simple sediment sluice, which may be gated or provided with an earth embankment set to breach during larger floods. We align the canal intake to minimize the flow diversion angle, and we can consider if a mechanically excavated gravel trap is appropriate. We can have a Type C intake, which is higher cost structures. And there, it's like Type A, but it incorporates a sediment sluice, perhaps the curved channel excluder, if the sediment's coarse, to align the canal intake to minimize diversion angle. Consider mechanically excavated gravel trap or possibly a flushing sediment basin. And where high investment costs might be justified through reduced desilting costs, consider a Vortex Tube extractor settling basin system in the canal head reach. Here I've got a warning about right-angled intakes, because the FAO's 2002 Irrigation Design Manual recommends right-angled intakes for sediment-laden rivers. However, physical and numerical models and field experience all demonstrate that frontal intakes, i.e. those with small diversion angles, will divert the minimum of bed sediment into the canals. Right-angled intakes increase the amount of sediment entering the canal. You can see it on this diagram. It's because the slower bottom flow, which carries the most sediment, is most easily diverted into an intake. Here we have a typical layout of a curved channel sediment excluder, which has a weir to provide some driving head for the sluiceway. The curved channel excluder has a guide pier which creates an artificial bend which encourages the cleaner surface water to go towards the canal and the coarser bed sediment to the inside of the bend where it will go through the sluiceway. We have a skimming weir separating the head regulator from the sluiceway. Here's a photo of a skimming weir. It's not a curved channel excluder, this one, just a straight skimming weir, but you can see here we have the sluiceway, and the weir provides a noticeable step. In this example, it even has a little ledge to reduce the amount of the sort of bed load that goes into the head regulator. This slide illustrates the vortex tube. The principle is that the bottom flow with the highest sediment concentration drops into this tube in the canal bed, where there is a vortex flow that carries this water and sediment laterally out to the side of the canal. This is a photograph at low flow. The vortex tubes, in this example, there are 3, each with a pipe going to the side, so each covers a certain width of the canal bed. You can see how the water will drop into the slot and then get carried out. Basins. Gravel traps and sediment basins have a mixed performance record. Flushable basins have worked well, but they're expensive and the farmers may object to the loss of water for flushing. Excavated basins tend to fill up and be forgotten because of the problem of cleaning. And during small floods, the basins will trap finer material which would otherwise pass through to the fields. And because you need dry conditions to clean excavated basins, it may not be feasible to clean them before the next flood comes. So, with the sediment passed to the fields, it means that we can spread the sediment load, or the problem, widely. But we do end up with a field rise due to sediment deposition, and this is worst at the upstream end of the system where they normally receive more water. Then we get a problem with upstream farmers trying to irrigate what have become high fields, and this can delay the downstream farmers from receiving water. The key measures to address field level rise are firstly, on the upstream fields, allow water to pass over as a sheet flow to reduce sediment deposition due to ponding. Then to supply the higher fields from another higher canal, which won't always be feasible. We can excavate material to reduce the field level, and we can raise the canal. Now, we'll talk about diversion objectives. So our objectives when planning a diversion structure are to make maximum use of the floods, to divert the floods but to avoid diverting excess flows that can damage the canals or fields, to minimize the diversion of coarse sediment, to be simple to operate under flood conditions, and be simple to maintain. We also need to understand and appreciate the farmers' priorities, which may not always be the same as the engineers. So, do the farmers want protection against floods damaging their canal system? Do they want to be able to stop the flow of water into their canals, which they may consider to be a loss of flow? Do they want to divert all the wadi flow or only part of it? Working out the capacity for a diversion structure can be done using this little formula. Q equals 2.778 AI times W over T, where Q is the discharge, AI is the irrigable area, W is the gross depth of irrigation after allowing irrigation efficiency, and T is the time when enough water can be available for irrigation, basically when the wadi flow exceeds the intake capacity. We need to look at design floods. because any engineered structures built in the wadis need to withstand severe floods with minimal damage. The common criterion is to design a flood to withstand flood of a specified probability, such as 1 in 100 years. However, there is a probability that one or more flood events that are greater will occur during the design life of the structure. This chart relates the probability of floods to the design life. This point represents a 10% probability, that's that dashed line there, of a 1 in 200 return period flood occurring during a 20-year design life. So you can see the risk of bigger floods for a specific design period and probability. So what are the consequences of having a larger than design flood? First consideration is, will the structure be damaged if it is submerged? Will canals be destroyed due to excess flow through the intakes? Also, designers need to be aware of the behaviour of high velocity water. If fast flowing water slows down, then kinetic energy of water may be converted back to potential energy and give higher water levels. This photograph illustrates what can happen when a high velocity flow hits an obstruction. And what we're seeing is the water actually can rise here, big splash, rising up about a metre in this case, simply as that flow energy is getting converted into energy where the water rises. This slide illustrates an unsatisfactory layout for a diversion structure. There's a weir here and an embankment that goes across, closing off the wadi, zigzag shape. So if a big flood comes, it's likely to go straight onto one of these embankments and the water level will rise, which might explain why in this case these embankments were overtopped. This photograph shows a flood greater than the design on a weir. Water is splashing over the wall here. Freeboard is very much reduced at the weir crest, but there's no damage to the structure itself. To do a structure design, we need to work out some rating curves which relate the flow to the water level. We will need rating curves for both upstream and downstream of a structure. And what the rating curve does, it's simply the level as an absolute elevation against the flood flows. And we can note on the graph then the different return periods of the flood flows. That's 1 in 50-year flood, for example, there, which is a higher water level than the 1 in 10-year flood. Command. We need to make sure that our diversion structures can provide sufficient command of the land to be irrigated and include provision for rise in the land due to sediment deposition. Structure needs to enable sufficient slope in the canals to allow for satisfactory sediment conveyance, and also any head needed to operate sediment removal facilities, if there are flushing basins, for example. Traditional diversion structures are just relocated further upstream as needed to maintain command of the irrigated land, but this is not feasible for an engineered structure. Single intakes. Now, cost-wise, it often looks better to provide one single intake for an irrigation system. However, this creates a number of disadvantages. If there's a single intake, it can create potential conflicts between groups of farmers over the sharing of water. The use of one or few intakes inherently gives greater power to the upstream people on each canal to take whatever water they want whenever it is flowing. Canals with sufficient capacity to serve the whole irrigated area will need to be quite large at the upstream end and therefore relatively expensive to construct. And any upstream diversion structures will receive the greatest amount of incoming sediment in the wadi flow. Diversions further downstream, where the wadi is flatter, will tend to have lower sediment content in the water. So, multiple intakes, they can achieve a higher overall diversion efficiency than a single intake. They provide more opportunities to take water, and any sort of flows used for flushing or above the capacity of the upstream intakes, you can then capture further downstream. It's also worth noting that weirs with intakes on each bank are not recommended, but are less vulnerable to problems than having an intake on one side with an inverted siphon to take water under the wadi, because the siphon will need very effective sediment exclusion to avoid the risk of blockage. They have worked in Yemen with combined with flushing sediment basins, but it's an expensive solution. This is a layout of the Wadi Tuban irrigation scheme in southern Yemen. Each of these is a weir. I think there is 11 altogether, and then each of these is some canal coming off, a lot of them in between the weirs. So there's more than 20 different intake points along the whole system. So you've got lots of little self-contained, effectively, irrigation schemes. And very rarely does any water pass through the system to the sea. Selection of intake sites. Where feasible, intakes should be located on the outside of a moderate bend where the channel bank is made of firm material. The deepest part of the wadi channel is also going to be at the outside of the bend, so it is easiest to divert the lower flows. The bend will cause the cleaner surface water to move towards the intake and the bed sediment to move away from the intake due to the helicoidal flow pattern. However, helicoidal flow is going to be less well developed in wide, shallow wadis than in normal rivers. There will still be the tendency for low flow channels to be at the outside of bends. We need to consider operation and maintenance early in the design process. Firstly, fewer and larger gates are likely to be easier to operate, and they're less vulnerable to blockage from trash. We need to have some clear gate operating rules, which can have some simple indicators of when gates should be operated. We need to have something that is easy and simple to maintain. And the design and performance of the intake is going to affect that ease of operation and maintenance, which will impact on the canal system. And the design of the canal system itself must take account of the operational characteristics of the intake. Here are the two types of traditional diversion structures. One is an an embankment across a wadi which blocks the whole flow. That's more appropriate in the downstream part of the system, where the flows in the wadi are occasional and relatively small. Or we can have a deflecting spur that diverts part of the flow down a canal, not the total flow. This is more appropriate upstream, and the spur condition can be adjusted to reflect the proportion of flow to be diverted. Both of these are vulnerable to damage by large floods. They are both relatively inexpensive to rebuild compared with the cost of building an engineered structure. So here we have a gravel embankment across a wadi pushed up by a bulldozer. Maybe once in 5 years there's a flood and all the water will get captured. Here we have a brushwood spur that is a deflecting spur trying to take part of the flow. This is vulnerable to damage, and after each flood the farmers have to bring more brushwood to repair it. Now, it's worth emphasizing the advantage of low-cost intakes is that they can be easily reconstructed at different locations to follow either the main wadi flow channel or to provide additional command. Engineered structures lose this flexibility because it is not attractive or feasible to relocate them during their design life or beyond. So the structure tends to remain intact but is increasingly ineffective. Now we'll look at different types of intakes. This is a simple improved intake, which is basically a rectangular opening. It provides a constriction and will reduce the maximum flood flow entering the canal here. This way to the canal. Here we have a simple layout of an improved traditional intake where we have some sort of orifice, perhaps with a gate, into a canal. We may have a sluiceway. We have a little spur here with an armoured head. So that's designed to capture just part of the wadi flow, maybe less than a fifth. We put it here so it is no more than a fifth of the width of the wadi channel. We can put here possible bed bar, which is effectively a very low weir, a wall in the wadi bed that cuts off any low flow channels from going round the structure. So it will encourage the low flows to go into this area where it can either go into the canal or through the sluiceway. And using a sluiceway can help maintain a channel towards the intake. Here's an actual drawing of a similar structure with the armoured spur. This can be built as a spill weir, probably protected by gabions over part of the length here. So an excess flow can spill back out into the wadi. We've got a sluiceway here. We've got a gated canal intake. Here's an example of the intake. This one, it doesn't have a big spur. It's got a little bed bar, a low weir in the wadi bed. It's got gates so that can be closed if it is not the farmer's turn to take water. This intake is an ungated orifice. In fact, the farmers will provide a gravel embankment in front of the intake if it is not its turn to take water. It will be done by the downstream farmers. When it is their turn, they block this intake further upstream. But the orifices, there's actually 3, will restrict the maximum flood flows that enter the canal. Here, on a properly engineered structure, is a sluiceway, and it's worth noting on this design, sluice gates are here, but there is no breast wall provided. So trash can either go over the gates if they're closed, or if the gates are fully opened, they can be lifted well clear of the water, and the trash can flow downstream rather than block the structure. This aerial view shows the problem of having one weir here. There's a bead. What is a bead? Weir 3 weir with a breaching bund here, but it supplies 2 intakes. This canal is bigger than that one, but the farmers have had to construct an embankment, goes upstream like this, to try to divide the flow in proportion between those 2 intakes. So the division point here is about 400 meters upstream of the weir. And this will get moved around from year to year, even between floods, to try and maintain the flow sharing. Not an ideal solution, but it is better than, in most cases, trying to divert water on one side and take it under the wadi to the other side. This design, also in Wadi Tuban in Yemen, is an innovative design showing a central breaching bund here and 2 inclined weirs which lead the flow towards the intakes on each side. Seems to be working quite well. The inclined weirs not only lead the water towards the intakes, it means you can get a longer crest length within a wadi width. This is another similar solution with a quadrant weir. Curved weir here, so a longer crest length than would be achieved in the channel width, and that quite nicely guides the flow to the intake and the sluiceway. Divide walls are quite often on irrigation intakes, but have been found to not be beneficial, because this divide wall will separate. The flushing flow in the sluiceway cannot flush the sediment collected in front of the weir here. This example from Wadi Zabid in Yemen is here is the divide wall in 2004. Here is a couple of years later, when that wall had been cut off or truncated, and you can see now that there is a quite substantial flushing flow to get sediment away in front of the weir, which all helps make sure that the water will come towards the intake when there's a flood. Word on under drainage, because under drainage is an alternative to providing sufficient mass in a structure to resist uplift pressures. This is a drawing of one of the weirs in Wadi Tuban. It's an unusual sort of 2-stage weir design. The crest is up here, then it drops, and then it goes down another slope, then down to the bottom here. The actual wadi bed level is up here somewhere. So this area is buried, or partly buried at least. But the actual thickness of the structure is quite small. Only 0.5 meter or so in this area. And they have drainage holes here and here to relieve any pressure. Here is a photograph of the weir at the bottom. Yes, those drainage holes are working even after 30 years. And in fact, the wadi can be dry at the weir upstream, but the subsurface flow will still come out through these holes. So, conclusions from this talk: design of intakes and diversion structures should consider, firstly, how to manage the potential sediment problem, how to provide command of the irrigated land for at least the design life of the structure, preferably more, how the structures will be operated and maintained, and then have a design that can balance function and durability against cost. Thank you.